Welcome. In this section, we'll be taking a look at what is called the chi-square test of independence, which is a hypothesis test that checks whether two variables are likely to be related or not. So let's take a look at an example. Suppose that a new post-operative procedure is administered to patients in a selection of hospitals. A researcher claims that doctors feel differently about this new procedure than nurses and decides to test her claim. All right, so our null hypothesis in a test of independence will be that there is no relationship between the variables of interest. So in this particular case, there is no relationship between opinion on the new procedure and the profession of the person you're talking to. So said another way, we would call these variables independent. So the chances, sorry, let me spell this correctly, independent. The chances that one of the professionals likes the new procedure would not be affected by knowing if you're speaking to a nurse or a doctor, because nurse or doctor is not playing a factor in how they feel about the procedure. So that's what it means for those variables to be independent. The alternative hypothesis, which is our researchers' claim that they're testing, is that there is a relationship between opinion and profession. So in that case, we would say that the variables are dependent. So as always with hypothesis testing, we assume the null hypothesis is true and then go out and collect data to see if we've got enough evidence to reject that null hypothesis. So to gather evidence, the researcher collects some data from some nurses and doctors, and that information is shown in this contingency table, which is simply a table that keeps track of two variables. So one variable being if we're talking to a professional that's a nurse or a doctor, and then the other variable being their opinion on the procedure. So in this case, for the nurses here, 90 liked the new procedure, 90 preferred the old procedure, 20 had no preference. So if I total all the nurses in this particular study, that would be 200 nurses. And then for doctors, 110 liked the new procedure, 60 preferred the old, 30 had no preference. If we add those, that will actually be 200 again. So 200 nurses, 200 doctors in this study for a grand total of 400 people. All right, let's also do some totaling. Out of those 400 people, the total that preferred the new procedure, 90 plus 110 would be 200. And then for the old procedure, 150. And then finally 50 had no preference. All right, so the O there stands for what they observed when they collected their data. And then our next step is to say, if the null hypothesis is true, that there is no relationship between the variables, what would I have expected the values to be in each of these cells of my table? So that's our next step. So let me focus on doctors. So if opinion and profession are independent, how many doctors would we expect to prefer the new procedure? So I'm looking for this expected value. So before I do it with the formula, let me just kind of go through some logic here. So forgetting about profession, what I see in this study is out of 400 people, half of them, 200, preferred the new procedure. So based on this data, if we talk to a person, there's a 50% chance they preferred the new procedure. All right, so that means that it doesn't matter if I'm talking to a doctor or a nurse. If I talk to 200 people, I would expect half of them to prefer the new procedure if profession had no influence over opinion. So half of 200, I would have expected 100 doctors to say they prefer the new procedure. So I did give a formula down here for it, We will not need to use this formula in the future. We're going to take advantage of technology in a moment, but I'll just show you how I got that 100 using the formula. So if I took the row sum, I'm going to highlight there, that would be the doctor's 200, and the column sum, the new procedure total 200. If you multiply those together and divide by that grand total 400, that will give us the 100. And let me go ahead and bring up my calculator here just to step through that. So if I took 200 times 200, divided it by my grand total 400, I would indeed get 100. All right, so we would do that process for each entry in this table. And I'm going to just fill these in. Again, we're not going to have to do this part by hand coming up, but these will be our values if profession is not a factor in opinion on the procedure. So the way the chi-square test for independence works is we look at the differences between what we actually observed when we collected data and what we would have expected to happen if the two variables were independent. So I can see here that there's differences between what we observed and what we would expect. So the chi-square test looks at those differences, and essentially, if those differences are very large, it's leading me to believe that, in fact, there is an influence of profession regarding opinion on the procedure. So let me show you how to conduct the test using technology. I'm just going to mention here that I did give the formula by hand for the test statistic or test value equivalently. So it will be a chi-square variable, and it's based on looking at observed minus expected. So in each of these cells, we would have observed minus expected, and it gets squared, and there's some division here, and that sigma there means we would do this process for each cell of the table. So the by hand formula here is shown for reference, but I'll show you how to get this on your calculator. So we'll go back to our chi-square distribution, and I'll show you graphs coming up, but let me get you through the details on the calculator. All right, so step one, we've got to get the observed data into a table on our calculator called a matrix. So you may have worked with matrices before. If not, you can just think of them as a table. So what we'll do on the calculator is you're going to look for matrix. So to activate matrix, you'll have to hit your second button and then matrix. And you're going to see the following. So matrices are often identified by capital letters at the start of the alphabet, like A, and we'll be using matrix A to enter our data. So you're going to have to come over to Edit, hit Enter there, and we have to tell the calculator the size of our matrix. So size is determined by how many rows of data we have. So we have 2 rows, and we have 3 columns of observed data. So it's called a 2 by 3 matrix. So I'm going to enter 2, hit enter, 3, hit enter, and then you're going to see your matrix. So we're going to step through and put in all of our observed values. So we'll enter 90 and then hit enter, and this will move you through the cells of the matrix or the table. So 90, 90, 20, and you hit enter, it'll bring you down to the next row, 110, 60, and 30. And if you make a mistake, you can use your arrows to go through that table and correct anything. So that is the observed data, and then we're ready to run the chi-square test of independence. So next step, we're going to hit our stat button, go back to our tests, and then I'm going to scroll quite a ways here past it so you can see you're looking for chi-square test. So we'll hit enter there. Now, we're never going to have to change anything on this screen, so we'll always put our observed data into matrix A, and then the calculator will actually calculate the expected values if the variables are independent and store them in another matrix, in this case B. So that value I calculated in the table that I expected 100 doctors to prefer the new procedure, each of those values would be stored in the calculator. So again, we're not going to need them directly because I'm not going to do the by hand calculation. I just showed you those to demonstrate what the test is looking at. So don't change anything on this part of your screen. And then we'll just go down to calculate. And that test value or test statistic is at the top, and then you'll see your p-value. And remember, for chi-square distributions, there's an associated degrees of freedom. So that is also provided. So let's go ahead and write down this information. So test value, or I just did test statistic this time. Again, they're the same thing. So it's a chi-square value. And it happens to be exactly 10 in this case. A little unusual to get a whole number there, but there you go. And then degrees of freedom, 2. So the formula for degrees of freedom is a little different than what we've seen before, but again, we'll just write that down based on the calculator. And then the p-value for decimal places will be 0.0067, which is a pretty small p-value. I'll write it as a percent. So 0.67%. So we're going to use a 5% significance level. So that is certainly less than or equal to an alpha of 5%. So our p-value is low, so we let the null go. So we do have pretty strong evidence against the null hypothesis, and therefore there is enough evidence to support the claim that opinion on the new procedure is dependent on the profession. All right, so that is how we conduct the chi-square test of independence. And coming up, we'll do a couple more problems, and I'll also show you the graphs as well.